Hello everyone, welcome to our new module in Applied Mechanics APMS 210. You're with me, Mr. C. Daka. I'll be your lecturer in this physics module from the Department of Applied Studies in the Malawi Institute of Technology, MIT, from the Malawi University of Science and Technology, MAST. So first things first, in this module, our aim is to introduce the basic principles of mechanics to students. By the end of the day, we expect that students should be able to apply vectors in resolving engineering problems and also to analyze forces, work, power, and energy in physical phenomena that involves these aspects. And also we expect students to be able to solve problems dealing with moving objects. So in this way, students should be able to determine velocities, speeds, and acceleration of such moving objects. And we also expect students to have the ability to explain the basic principles of machines and also some of the machine elements. That is it about it. So this module basically is a physics module. That's why it's called Applied Mechanics. However, for us to deal with this module, we have outlined 6 topics. To begin with, we're going to deal with force systems, moment, couple, equilibrium, and some application of force systems. And then our second topic will be stress and strain. Here we'll deal with direct and shear stress-strain relationships. We'll look at the Young's modulus, and we're also going to look at the modulus of rigidity G. These are our elastic constants. So we'll be dealing with such systems that involve stress and strain. Our third topic will be angular motion. As the name suggests, these are motions that involve circular orbits, motions that involves a looping type of phenomena. For example, if you tie a mass on a string and then you swing it above your head, the mass takes a circular path, and that becomes angular motion because it's got angular velocity and angular acceleration. And we can relate the same to the linear components of the angular velocity and the linear components of the angular acceleration and angular displacement with regards to the angle theta and the radius of the motion r. Our fourth topic will be dealing with work and energy. We'll deal with work diagrams and work that is being done by a force, the forms of energy and how power is transmitted by a torque. Our fifth topic will be dealing with machines. That includes mechanical advantage, velocity ratios, efficiency, the laws of machines, machine calculations, etc., etc. Finally, we'll be dealing with hydrostatics. Here we'll be dealing with type of fluids, the transmissibility of fluid pressure, pressure measurements, hydrostatic forces, variation of pressure with depth. We'll look at how a barometer works, and we'll deal with center of pressure, and we'll also be able to look at how thrust is brought about on a plane, especially on a vertical surface. In order for us to successfully accomplish the outlined topics and to get to the bottom of the physics behind such phenomena, we will be using the prescribed text by William Bolton, 2006. That's the 5th edition, and we also have few more recommended texts as outlined below in the PowerPoint presentation. So this module will be assessed in two phases. The first assessment will constitute 40% of the module assessment. The 20% will come from the assignments and quizzes, which will be issued out at designated intervals, depending on the amount of work that has been covered and concepts that are being assessed. And the other 20% will come from the tests that will be issued. Details regarding the same will be announced at a later stage. And 60% will be the end of semester examinations, which is usually a 100 marks examination paper, and it has to be seated for 3 hours, and that constitutes 60% of the total module assessment. So that is it about the course, a preliminary introduction. However, we're not going to go into the nitty-gritty content. I would rather help us to have a recap of what Introduction to Mechanics is all about. So when we look at mechanics, we're dealing with the state of rest or motion of bodies subjected to the action of forces. So you can imagine any other thing as an object. For example, these days, almost everyone has got phones. A phone is an object, right? You can put it on the table, it can stay at rest. It means it's an object at rest. That's mechanics. If you take the phone in your hands away from the table, it means you're bringing in some motion from one position, which was on the table, into some position in your hands. So that's some motion, right? You're subjecting the body, which is the phone, to your force exerted by your hand. And that becomes some mechanical phenomena. So mechanics is basically divided into these three subcategories. We look at the mechanics of rigid bodies, okay, and we look at the mechanics of deformable bodies, and we look at the mechanics of fluids. All right, yeah. So fluids have got their own mechanics, their own theories, rules of the game, how fluids behave, and of course some phenomena like some phenomena were explained, but some phenomena still leaves a lot of room for discovery and explanation, like the issue of turbulence. You know, turbulence is one of the issues, and it affects flight navigation systems for airplanes, helicopters, and most of the airborne mechanical systems. So our focus will basically be at rigid body mechanics, because we're dealing with the statics and dynamics. But for a start, we'll start looking at statics, where we're looking at bodies that are in equilibrium. For example, if you put your phone on a desk, it is stable there, it is just lying on the desk. That means the phone is in equilibrium. The forces that are acting downwards on the table are the same forces that are acting upwards on the phone. Action-reaction forces. We'll look into it as we look at the Newton's laws of motion, especially the third law of motion that looks into action and reaction forces. In dynamics, we look at accelerated motions. If you take a stone in your hands or a pebble by the riverbank and you throw it up in the air, it means the pebble has got some acceleration. It's moving from the position which was initially in your hand into some other position in the air. It means it's being accelerated. So there's got to be some dynamics there. So you can look at the 2D dynamics, XY, all right, where the X motion becomes the horizontal motion and the Y becomes the vertical motion. Or you can look into advanced dynamics, where you look at the motion in different directions, X, Y, Z, you know. Yeah, but we'll not look into advanced tensor kind of vectors, where we have 4 or 5 dimensions, like in the case of space-time, etc., etc. So the fundamental concepts that we're going to be dealing with basically includes the basic quantities, the length, the time, and the mass. These are the things that you've dealt with in your preliminary introduction to physics in your first year. So this is pretty much of a recap, trying to get back to the basics. And then we're also going to be dealing with force, because we're going to deal with the work being done by force, etc., and how force can move objects, motion brought by forces, etc. So in this case, you can either have a direct contact force. When you take a phone on the desk, when you pick it up with your hands, that's a direct contact. You have to touch the phone and pick it, and then you've exerted the force. And you have got what we call force at a distance, or a remote action force, a force that doesn't need a direct contact. A good example is magnetic forces. All right, for an illustration, if you take one magnet with the north pole, the north pole of a magnet and the north pole of another magnet, you lay them down aligned together on a disk. Once you start pushing the magnet towards the other magnet without having them to physically contact each other as two distinct bodies, the magnet begins to exert forces on each other, and motion in one body translates into a motion in the other magnetic body. In that case, it means you have got a force at a distance, or you've got some remote action. This is seen in the case of gravitational forces. That's the same way the Earth is attracted by the sun to be in that perfect elliptical orbit that makes a year and changes the seasons as we go along the year. And the same applies with electrical forces, electrical charges. All right, electrical forces. So when you have 2-point charges with a positive and positive, they pull each other apart without necessarily touching. When you've got negative charges, they pull each other towards each other, the negative charges, without necessarily getting into a physical contact. So these are remote action forces, or forces at a distance. So ideally, we're going to deal with rigid bodies, but for argument's sake, let's also look at the particle. A particle is it's a point-like mass with very negligible size. We don't consider any volumetric or space being occupied by a particle. We just consider it as an ideal entity with very negligible size, but which can assume any mass assigned to it. Rigid bodies, we're dealing with bodies that undergo no deformations. So at any point in time, the relative distances between two particles within the rigid body remains the same. And then we also deal with the concepts of concentrated forces. However, because we're dealing with the basics, let's have a recap on quantities that we have. We have scalars and vector quantities. With scalar quantities, we deal with magnitudes only. So if you're looking at speed of an object, it means you're only dealing with the magnitude, like 30 kilometers per hour. But if you're dealing with the velocity of the same object, 30 kilometers per hour at 60 degrees, that becomes a velocity. 60 degrees determined by the angle theta is the direction. 30 kilometers per hour being the magnitude, it becomes the magnitude of the vector. So the vector is constituted of two parts, the magnitude and the direction. But once the direction is lost, it means it becomes a scalar. So speed is a scalar and velocity is a vector. And these vectors, they come in different forms, and we're going to deal with them as free vectors, sliding vectors, and fixed vectors, depending on the vector diagrams and illustrations we're going to have and the phenomenal circumstances that we're going to look at in mechanics. So a vector can be represented by the uppercase V with a line bar on top of it, something like an arrowhead. Okay, that shows the direction. That means that's a vector quantity, as seen here. So the size of the length of the vector becomes its magnitude, and the angle theta becomes its direction. So there are a couple of operations that we handle when you're dealing with vectors. One of it is what we call vector addition, and that constitute vector sums and vector subtractions. So we look at triangle law and the parallelogram law, where we look at a vector being constituted of components, all right? For example, a vector v being constituted of a component v1 and v2. So in that scenario, it means the resultant vector v is the sum of the two vectors. However, we don't add vectors as 1 plus 1, 2 plus 2, because these are components. So we use this triangle rule and the parallelogram law to determine the components and to properly resolve the components into their vector additions. So we add the xx, the yy components respectively. The same applies with vector subtraction. This is just about direction. In which direction is the net vector going into? So that gives us an idea of whether the resultant is a negative or is a positive, depending on the space orientation. If you remember the XY plane, and we have the 4 quadrant, so depending on which quadrant and which magnitudes are we're dealing with, you'll be able to get a negative of that vector and a positive of that vector, but it's nothing but the direction. It is also determined by the angle theta, because theta clockwise becomes a positive theta, and the theta clockwise becomes a negative theta. So it's all about that. However, in order for us to fully appreciate, because not all the vectors come with their components as a proper right-angled, illustration, like in the case of Pythagoras theorem, where it's easy to do the math. We use the cosine rule and sine rule to determine the angles and sides of any given system of vectors, a vector with its components. So in that case, we use the cosine rule as shown here, and the sine rule, where the ABC in caps are the sides and the ABC in small letters are the actual angles subtended by the components and the vector. So like we said, that's how we resolve the components into the x and the y's. However, another important aspect of vectors is the unit vector. All right. So this unit vector, suppose you have got a 3-dimensional space shown by this cube down on the bottom, on the right bottom here. It means that you have the vector in the x, vx, vy, and vz. And those components, x, y, z, are forming a resultant vector v, all right? But what's the direction of v? It means v has got a direction determined by x theta, theta x, theta y, and theta z, all right? So all these 3 thetas, theta x, theta y, and theta z, are determining the direction of v. In other books, in the learning resources, you see that the angle theta x, theta y, theta z are represented by alpha, beta, and gamma. It's pretty much the same concept. Yeah. So in this case, the direction is determined by the unit vector n with an arrowhead, or neta, or whatever it is, n with an arrowhead. And it is dimensionless. What it does is that it maps the precise relationship between this theta x, theta y, and theta z, so that the direction of this v is properly mapped by these theta components, or these individual directions. So other operations include the dot products, or what we call the scalar product, or vector, and we also have the cross product, or the vector product. So the dot product of 2 vectors, it's equal to the multiplication of the magnitudes of the individual vectors times the cosine of the angle theta between the 2 vectors. So we have got the vector q and p subtended by the angle theta. So if you take the magnitude of P by its length and the magnitude of Q by its length, multiply them, and then take the cos of the angle theta, that gives us the dot product as seen here. So we can look into the mathematics, but it's pretty much easy to get. So you can make cos theta subject to the formula. So given the knowns, the dot product, and the multiplication of the magnitudes, you can get to know the angle theta between the two vectors. So the cross product is pretty much looking at sine theta instead of the cos theta of the two angles, and you take the magnitudes of the combined product of the two vector entities, and then which is equal to sine theta times the magnitude of the individual vectors. So in this case, we deal with matrices. When it comes to cross products, we deal with matrices, and for simplicity, we deal with three-dimensional matrices, 3 by 3 matrices, IJK and PX, PY, PZ, XX, QX, QY, QZ. So this is a three-dimensional matrix. So we get matrix rather, a three-dimensional matrix. So we can take the determinant of this and get to know the cross product. Yeah. However, because now our focus is on mechanics, one of the prominent scientists in the field of mechanics, the earliest prominent scientist is Isaac Newton. Yeah, so precisely Sir Isaac Newton. So he came up with the laws of motion divided into 3 in his book Mathematica. In short form, but in English, in full form, it's Mathematical Principles of Natural Philosophy. It's one of the transformational books of all times in the history of physics and science. So we give all the credit to Sir Isaac Newton for his contribution to the foundational principles of mechanics. So the first law is basically a law that deals with how a body is reluctant to move when it's at rest, and how it is reluctant to stop moving when it's moving, and it's usually referred to as the law of inertia. So let's say when you're seated on a chair and someone's trying to move you up, you drag, you're relaxed, you resist the motion. So that's the law of inertia. And let's say you're running and someone just want to hold you by the hand, you easily slip away from their hands because your body wants to continue its state of motion. So a body, it's either wanting to stay at rest, or wanting to maintain its constant velocity in a particular direction. So the second law of motion deals with the change in the rate of change of momentum of a body, and it says that the rate of change of momentum of any object is equal to the net force that is acting on that particular object. It means to say that when a body changes in momentum, it means it changes that momentum in a particular time, and that becomes the force that is causing the change in momentum. And if you do the math, you end up with a formula that says the net force of a body is equal to its mass times acceleration. So the acceleration is the change in momentum. The ma is the rate of change in momentum. The mass times acceleration, the rate of change in momentum. So we also look at the third law of motion, and this one is very important when we're dealing with equilibrium systems in mechanics, and especially for applied mechanics. So we look at different free body diagrams that illustrate equilibrium systems. So in this case, the third law of motion looks at what I call the action and reaction, to say for every force acting on a body, the body being acted upon produces the same amount of force towards the body which is acting, but in the opposite direction. So for example, if you push a wall all right, you end up moving backwards because the amount of force that you push on the wall is the same force that is reacted on you by the wall in the opposite direction, and then you move backwards. So you push the wall pushes you back. You act on the wall reacts on you. So for example, the pushing could be force A acting on the wall, and the wall could be a reaction, force B, acting on you, the pusher. Yeah, so that's it about the Newton's third law of motion, and this is fundamental in most systems that needs action and reaction. For example, when you're looking at rockets, all right, when there's combustion in the combustion chamber of a rocket, the the exhaust thrust moves downwards out of the rocket engine, but the same downward motion is exerted on the rocket, and the rocket propels back, up. That's why you see that there's the exhaust of a rocket, let's say spaceship or a rocket or any ballistic missile, the exhaust moves in the opposite direction, and the missile or the rocket moves in the other direction because of action and reaction. Yeah, so the action by the exhaust produces a reaction on the object or the rocket. Yeah, so this is very fundamental, and it's very important in aerodynamics and ballistics. We're also going to just have a recap of the Newton's gravitation law. Basically, here we are dealing with the gravitational forces in very massive entities. You know, gravity exists everywhere where there's two or more bodies, but it's very much negligible. But when the mass is really big, as seen by this formula, when the two masses are really big and pretty much close together, the force becomes really huge. And that's why gravitation forces is usually a factor when we're looking at planetal objects and cosmic objects like planets, you know, the planets. When you look at the black holes, you know, very massive things, the stars, yeah. So because they've got very big masses, this is because the gravitation constant is very small, it's 10 to the power minus 11. So this is very small. So for a small mass like 20 kgs, it's negligible gravitational force. That's why we don't experience. But however, there is gravitational force. When you stand close to your friend, there is gravitational force, but you just can't feel it because it's just pretty much negligible. You can't feel it, you can't know it exists. However, when you're standing on the surface of the earth, all right, with your little mass m here as seen by this weight formula, with your little mass m and a huge amount of mass me of the earth, you begin to feel the force. When you jump up, you get down, you're pulled down because now you're dealing with a huge mass, which is the earth. So gravity begins to take play in that instance whenever we have got a big mass. So on earth, the weight can be recalculated if you rate g, which is the gravitational acceleration on the surface of the earth or near the surface of the earth, to be equal to the gravitation constant times the mass of the earth and divided by the distance, the square of the distance between the body on the earth, let's say you yourself on the surface of earth, and the center of the gravitational force, which is the inner core of the earth. So we basically assume that the earth is on average a smooth surface. You know, I know people will be thinking about how about when you be on the top of Mount Everest, would you get the same amount of gravitational acceleration or gravitational force? No, the big answer is no, because at different distances away from the center of the earth, you've got different gravitational accelerations. I wouldn't precisely say how much it would be. It would need an experiment, but there's those values elsewhere. You can cross-check on the internet to see if you can get different values for different locations on different altitudes on the beyond the sea level. Yeah. So if we take G to be this GME by R squared, then in the weight of any object on the surface or near the surface of the Earth becomes the product of its own mass, which does not change anywhere in the universe, and times the gravitational acceleration, which is assumed to be constant near the surface of the Earth. So finally, we're going to be dealing with units, systems of units, and like we saw in the introduction, we said force is not a basic physical quantity; it's a derived quantity. So, for example, force force has got the unit Newton, which is represented by the capital or the uppercase N, and then the Newton can be re-expressed in terms of the basic quantities of mass, length, and time. So the Newton becomes the kg dot meter per second squared. Kg is mass, meter is length, and the second squared is time by time, dimension of time by dimension of time. So we're going to use what we call the SI units, the System International units, and this illustration of the Newton in terms of the basic units tells us that 1 Newton is the force that is required to give a mass of 1 kg, an acceleration of 1 meter per second squared. So this is just a recap. We did this in our first year, but it's just an introductory recap in order to get to know the basic things regarding mechanics. With COVID-19 going on, it's pretty much normal that some of us will have forgotten some of these things. So as a recap, before we get into the main content, it will be good for us to look into these things. And then finally, we are going to look at the prefixes. In science, we usually deal with very, very big numbers, and also we deal with very, very small numbers. All right. So because of that, we wouldn't really like it to be expressing these numbers as they come in their huge, narratives. No, we use what we call prefixes. So, for example, a 1 with, let's say, a 1 billion, okay, a 1 with 9 zeros, all right, becomes 10 to the power 9 in its exponential form. It means it's a 1 and the 9 zeros. And in its prefix form, it's giga, and the SI symbol for the giga prefix is G. The same applies to the mega and kilo. And when you look at the sub-entities, the very small things, we look at milli 10 to the power minus 3, it means 0.003. Micro 10 to the power minus 6, it means 0.501. And nano 10 to the power minus 9, it means 0, 8 zeros, and a 1. So these are the symbols M, mu, and N for milli, micro, and nano. So, however, this was just a brief introduction, and as we go along, we'll be solving problems to make a vivid picture of what we've been talking about: the dynamics, the statics, the equilibrium systems, the Newton's laws of motion, and how to analyze engineering problems that are involving systems in equilibrium, systems in motion, accelerated objects, rigid bodies, etc., angular motion, hydrostatics. Yeah. So that is it about the introduction lecture. If you've got any questions, feel free to send the same on the official forums on our Moodle platform. Thanks for your kind attention. I will leave you with the quote from Isaac Newton: "If I have seen further than others, it is by standing upon the shoulders of giants. I can calculate the motion of heavenly bodies, but not the madness of people." Wishing you the very best. Thank you.